The metal cylinder is worn, reinforced, and sealed at one end so precisely it looks less like a container than a machine part. And that is the first strange thing about it. It was built to move. Inside, it could carry up to roughly 600 letters. But that still does not explain why a mail container had to be built this precisely. Postal workers pushed the entire carrier into a pipe where its fit mattered because air pressure would send it through New York at roughly 35 miles per hour. On some journeys, a route that could take a mail wagon about 40 minutes could be covered through the tubes in as little as 7. And that is where this cylinder becomes harder to dismiss as a historical curiosity, because the obvious explanation is street congestion. Mail moving between postal facilities could be slowed by the city above, so the post office department created another route, one that avoided the streets altogether. But if that were the whole story, this would have been a clever local shortcut. It was not. The more I followed where cylinders like this were sent, the larger the machine around them became. The pipes eventually extended for approximately 27 miles, linking postal facilities across Manhattan and connecting to Brooklyn through the Brooklyn Bridge. So this battered cylinder was not simply moving faster than a wagon. It was moving through an underground network built around thousands of journeys like it. And that creates the problem. The system worked. It expanded. It remained part of New York's postal infrastructure across a span of roughly 56 years, despite interruptions. Then, in 1953, the remaining system ended, which means the question is not whether this machine functioned. We already know that it did. The question is how something fast enough to outrun the streets above it, extensive enough to stretch beneath the city, and useful enough to survive for decades could become too impractical to keep, and so unfamiliar that this battered cylinder now feels less like an obsolete mail carrier than evidence from a future New York somehow buried in its past. The first clue is still in the cylinder itself. Historical descriptions of New York carriers give dimensions of roughly 2 feet in length and 8 inches across, with an empty weight of about 21 pounds. A loaded carrier was not a lightweight message capsule. It was a substantial steel object that had to enter a tube only slightly larger than itself, accelerate through that tube, negotiate the route, and arrive without destroying either the mail or the receiving machinery. That helps explain details that otherwise look minor. Felt bands around the carrier helped close the narrow space between steel cylinder and iron pipe. The carrier did not contain a motor. It was the pressure difference around it that mattered. Air moving through the line pushed or pulled the cylinder, and the closer the carrier fit the tube, the more effectively that pressure could be used. Even its door belonged to the larger system. Postal designs incorporated mechanical locks so that an improperly secured carrier could not simply be launched into the line. What looks like an unusually overbuilt mail container begins to make sense once it is treated as one moving component inside a much larger machine, and that machine extended far beyond the pipe itself. At the stations, workers needed specialized transmitting equipment to introduce a carrier without destroying the airflow that moved the line. At the other end, receiving machinery had to slow the arriving cylinder and make it accessible without bringing the entire system to a halt. Large blowers and compressors, driven by electric motors, created the pressure difference. Historical post office records describe working pressures in the range of roughly 3 to 8 pounds per square inch. So the underground network was not a passive conduit. Every functioning route depended on a coordinated chain. Power machinery, sealed pipe, transmitters, receivers, carriers, switching points, maintenance systems, and people who knew how to operate all of it. That is the first major change in what this surviving cylinder represents. It is not evidence of a pipe. It is evidence of an industrial transportation system. And once that becomes clear, the next question is unavoidable. Why build something this elaborate for mail? The answer begins before New York's system opened. By the late 19th century, the United States Post Office Department was already examining pneumatic dispatch as a possible solution to urban transportation delays. Congress authorized an investigation into rapid pneumatic dispatch in 1892, and Philadelphia began operating an American postal pneumatic system the following year. New York followed. On October 7, 1897, a public test ran between the main post office and Station P in the Produce Exchange. The circuit covered roughly 7,500 feet, and contemporary accounts turned the opening into something more than a quiet engineering trial. Ceremonial objects went through the line. Government reporting mentions items including a Bible, an American flag, and a copy of the Constitution. Demonstration shipments also included packages and, famously, a live cat. The cat matters mainly because it reveals how the new system was being presented. It was not evidence that animals were routinely being mailed beneath Manhattan. They were not. It was a demonstration of physical capability. The message was simple. If the tube could move loads that seemed unusual, bulky, or alive, then ordinary sacks of letters represented a much easier problem. The celebrated public test took place on October 7th. Postal historical records date the start of New York service to October 15th. That distinction matters because what began as a demonstration quickly became an operating utility, and then it began to spread. On August 1st, 1898, pneumatic service across the Brooklyn Bridge connected Manhattan postal facilities with the Brooklyn General Post Office. That crossing reveals another detail hidden by the simplicity of a line on a map. Buried pipe rests in relatively fixed ground. A bridge does not. It expands, contracts, flexes, and moves. Postal engineers therefore needed special devices to preserve tube alignment across a structure that was never completely still. The rest of the city posed different obstacles. Historical descriptions place much of the New York tubing several feet beneath the streets, commonly around 4 to 6 feet deep, although actual depth varied with conditions. And beneath New York, those conditions were rarely simple. Sewers already occupied space. Utility lines occupied space. Rock occupied space. Rapid transit construction increasingly occupied space. A pneumatic route could not always travel directly from one station to another. It had to coexist with everything the city had already buried and everything the city continued building afterward. That makes the surviving system maps especially revealing. A map from 1914 shows a network already far beyond the original demonstration line. A later map from 1952 shows the system after decades of modification and continued use. Modern summaries often describe the mature New York network as approximately 27 miles in route length. A post office technical history gives a much larger figure, 55.5582 miles of tube. At first, those numbers look incompatible, but the infrastructure explains the difference. Major sections used paired tubes for traffic moving in different directions. Measure the path the network covered through the city, and the result is roughly the smaller figure. Add the physical length of the individual pipes themselves, including parallel tubes, and the number can approach twice that distance. The disagreement in the numbers therefore reveals something useful. There was not one pipe beneath New York. There were paired lines, branches, terminal equipment, and multiple postal stations connected into a transport system whose physical construction was larger than its route map alone suggested. And this is where the original cylinder changes again. Its precision was not simply necessary because it had to travel fast. It had to work reliably inside a network whose scale multiplied every weakness in the design. A poor seal was no longer a problem for one carrier. It was a problem repeated across miles of tube. A failure at one station could affect traffic behind it. A blockage could interfere with scheduled dispatches. A badly secured door could become a mechanical hazard. The system's strength came from repetition. So did its vulnerabilities. Postal employees assigned to the tubes became specialists. New York operators responsible for dispatching and receiving the cylinders became known as rocketeers. At one point, post office records identify roughly 136 of them in the city. Their work reveals something the maps do not. a carrier did not necessarily enter the system at one station and emerge at its final destination in a single, uninterrupted journey. At transfer points, workers could receive it, read the destination information, and send it into another segment. The network was fast inside the pipes, but it still depended on human relays. Under favorable operating conditions, carriers could be dispatched with remarkable frequency. Historical records describe rates around 5 carriers per minute in later service, about 1 every 12 seconds. That begins to explain how relatively small cylinders could collectively move significant volumes of mail. One carrier was limited, a continuous stream of them was not, and contemporary postal estimates make clear that the system was not marginal. A post office historical study reports that during scheduled operating periods in the 1950s, roughly 55% of New York City's mail moved through the tube network. Smithsonian historical material also gives a 55% figure for an earlier period in the mid-1920s. The dates attached to the statistic vary, so it should not be treated as one universal peak measurement. But the broader point is difficult to avoid. For significant periods, the tube network was carrying a substantial share of the city's postal traffic, which makes the criticism of it more surprising, because the criticism did not appear only at the end. It appeared almost from the beginning. Nationwide pneumatic service was suspended between July 1901 and June 1902 when Congress withheld funding. In 1907, a postal inspection report described pneumatic transportation as the most expensive method of mail transportation then in use, and questioned whether its advantages justified the expense. This was more than 4 decades before New York's final shutdown, so the system's eventual disappearance cannot be explained as a late realization that the technology had become obsolete. Government officials were already asking a more uncomfortable question while the network was still relatively new. What exactly was the post office buying when it paid for speed? To understand that, we have to return to the carrier. A museum canister is described as holding as many as 600 letters. Other historical sources describe New York carrier capacities closer to 500, and another Smithsonian treatment gives roughly 400 for one configuration. Those figures may reflect different carrier designs, periods, or assumptions about loading, but every version leads to the same physical fact. The carrier had a fixed diameter, the pipe around it had a fixed diameter, and no improvement in air pressure could make a large parcel fit inside an 8-inch tube. This became increasingly important as the postal workload changed. The expansion of parcel post exposed a basic limitation in the network. Letters and compact mail could move efficiently through the tubes. Many parcels could not. That meant surface transportation never disappeared. The post office still needed wagons and, increasingly, motor vehicles to move the kinds of mail the pneumatic system could not accommodate. And now the speed comparison begins to look different. If a carrier could move between 2 stations in 7 minutes while a wagon required 40, the tube clearly won that particular race. But the post office did not operate one race. It operated an entire chain of collection, sorting, transfer, railroad connection, parcel handling, and final delivery. The tube optimized one part of that chain. It did not eliminate the rest. A 1916 Post Office committee captured that contradiction unusually clearly. It acknowledged the 2 advantages that made pneumatic service attractive in the first place: high speed for limited quantities and freedom from street congestion. Then it listed the limitations: restricted carrier capacity, difficulty with parcels, intermediate handling, congestion under heavy loading, maintenance problems, the possibility that breakdowns could interfere with larger portions of the system, high expense, and the need to handle the mail again at points where the tube had delivered it quickly but not yet placed it where it ultimately needed to go. That last point quietly changes the entire investigation. The tube could win on travel time and still lose on workflow. Suppose mail reached a railroad terminal rapidly through the pneumatic system. If employees then had to remove it from carriers, sort it again, and prepare it for the next stage, some of the minutes saved beneath the streets could disappear inside the building. Speed through the pipe was real, but speed through the pipe was not the same thing as speed through the postal system. Once that distinction appears, several details that seemed unrelated begin to line up. The Rocketeers were not merely operators. They were part of the handling cost. The small carrier was not merely a clever engineering solution, it was also a capacity ceiling. The fixed underground route was not merely protection from congestion, it was also infrastructure that could not easily move when postal geography changed. And the elaborate machinery that made the network possible also meant that keeping it alive required constant attention. The tubes had to be lubricated. Postal records describe special perforated carriers filled with oil being sent through the lines to distribute lubricant. Carriers could become stuck, receiving apparatus provided indications when expected cylinders failed to arrive, allowing operators to recognize that something had gone wrong inside a section of pipe they could not see. Often, changing the air pressure could free the obstruction without excavation. Most blockages appear to have been handled this way, but not all of them. A small fraction required crews to open the street and reach the buried pipe directly, and maintenance was not risk-free. In 1903, a worker was killed after a damaged tube ruptured during repair testing. That accident should not be used to imply that the entire network was extraordinarily dangerous, but it does reveal the physical reality hidden behind the apparently effortless movement of a cylinder. This was pressurized industrial infrastructure buried inside a crowded city. It had to be maintained like infrastructure. And yet even after the criticism, the suspensions, the handling problems, and the cost disputes, New York's system refused to disappear. That matters, because if the disadvantages had simply overwhelmed the advantages, the history should have ended much earlier. Federal pneumatic service was shut down after World War I. Then, New York brought it back in 1922. The decision to restore service tells us that the advantages still had value. New York remained exceptionally congested. Its postal volumes were enormous, and the tube possessed one quality that trucks and wagons could not reproduce. It occupied its own path. When the streets became slow, the tube continued moving. When the streets became crowded, the tube continued moving. And during severe weather, that independence became even more obvious. The Great New York Blizzard of 1947 paralyzed large parts of surface transportation. The buried pneumatic network continued operating. In a city struggling to move through snow, the tube's 19th-century design suddenly looked extraordinarily resilient. If we stopped the investigation there, the ending would seem obvious: keep the tubes. But the post office was measuring something larger than emergency performance, and this brings us to one of the least visible parts of the system: ownership. Much of the pneumatic infrastructure was not simply federal property constructed and permanently owned by the post office department. Private companies built and owned major portions of the network, and the government contracted for the service. The Tubular Dispatch Company was involved in the original Manhattan system. The New York Mail and Newspaper Transportation Company became involved in the Manhattan-Brooklyn service, and later in Manhattan routes as well. Corporate relationships changed over time, including connections with the American Pneumatic Service Company and successor interests. The details are complicated, but the consequence for the post office was simple. The network was not only an engineering system, it was also a contractual system. The federal government operated postal traffic through infrastructure whose ownership and maintenance arrangements created recurring appropriations, negotiations, and disputes. That helps explain why Congress kept returning to the same question. Was the speed worth what the government was paying for it? And, by the middle of the 20th century, the alternative no longer looked like the horse-drawn wagon against which the tubes had first proved themselves. It was the motor truck. A truck was slower than a pneumatic carrier moving freely through a dedicated tube. But a truck could carry far more. It could take sacks. It could take parcels. It could change routes. It could travel directly between facilities that had never been connected to the pneumatic network. If postal operations moved to a different building, the truck did not require a new iron line beneath Manhattan. It required directions. That difference gradually undermined the central logic of the tube. The pneumatic system had been built to defeat the inflexibility of congested streets. Now, its own route had become inflexible, and the map that once demonstrated the network's power begins to look different. Every line on it represents access, but every line also represents a commitment, a fixed connection between specific facilities, a buried path that remained useful only while the postal geography around it still justified that path. This does not mean the network suddenly became useless. The surviving evidence points in the opposite direction. It remained capable of moving mail. It remained fast. It remained useful under particular conditions. The problem was that those qualities no longer answered the question postal managers were asking. They were no longer comparing a tube carrier with a wagon over one congested route. They were comparing two complete systems of movement. One was fast, specialized, mechanically complex, and fixed. The other was slower point-to-point, but larger, adaptable, and increasingly capable of handling more of the postal workload without transferring the mail between specialized containers. And before the final decision, the network had already started contracting. In April 1950, the pneumatic connection between Manhattan and Brooklyn was suspended during work on the Brooklyn Bridge. It was never restored. That is a significant change. The bridge line had once represented expansion, the moment when the system crossed from one borough into another. Now, the same connection disappeared 3 years before the rest of the network. Yet even this did not produce an immediate, total shutdown. Around 1950 and 1951, the government entered another long-term contractual arrangement with the New York Mail and Newspaper Transportation Company. That fact makes the final years particularly revealing. There was no simple moment when everyone agreed that pneumatic mail belonged to the past. Contracts continued. Operations continued. Postal workers continued dispatching carriers. Government officials continued measuring the costs. And eventually, the calculation moved decisively against the tubes. In 1953, Postmaster General Arthur Summerfield determined that the remaining New York pneumatic service should end. The Post Office Historical Study gives the comparison in remarkably practical terms. Officials concluded that approximately 2 additional trucks, costing about $25,000 per year, could replace the remaining tube service while avoiding a much larger lease expense. That does not mean the trucks could move a cylinder from station to station faster. They did not need to. They only had to replace the postal function of the tube network at lower total cost. That is the point where the original mystery resolves. The system was not shut down because its central mechanism had stopped working. It was shut down because the mechanism was no longer the central issue. The post office had changed what it was optimizing. In 1897, one of the urgent problems was how to move relatively compact mail quickly through streets that could not guarantee quick movement. A dedicated pneumatic route was an extraordinary answer. By 1953, the problem was how to move an increasingly diverse postal workload through a changing metropolitan network as economically and flexibly as possible. The same dedicated route now solved a narrower problem than the one the post office needed solved. On December 12, 1953, the remaining New York pneumatic service was suspended. New York was the last American city still using underground pneumatic tubes for United States mail. The workers did not simply disappear with the network. Roughly 130 postal employees attached to the service were reassigned. and the business relationship did not end as neatly as the machinery did. Correspondence and litigation records preserved from the aftermath show that cancellation produced contractual consequences that continued after the last carriers stopped moving. Then, the physical system itself began to retreat from view. Tube machinery was removed from postal buildings as space was needed for newer mail processing equipment. Historic American buildings survey documentation of the Grand Central Post Office Annex records that the old pneumatic loading machinery was no longer present there by the time of the later architectural survey. The pipes are harder to account for. Researchers have documented remnants and flanges in several postal buildings, and construction work has occasionally encountered old postal pipe. There is also a long-standing possibility that additional sections remain underground, but that possibility has to remain exactly that. There is no reliable basis for claiming that the complete network survives intact beneath modern New York. There is also no basis for claiming that every section was removed. The surviving evidence supports something less dramatic and more interesting. Fragments remain. The complete physical inventory does not. Which brings us back to the canister. At the beginning, its heavy construction seemed excessive for a mail container. Then, the network explained its shape. The close fit belonged to the air pressure system. The steel body belonged to repeated high-speed transport. The door belonged to the station machinery. Its capacity belonged to the economics. And its size, which first demonstrated how substantial the system was, eventually reveals one of the reasons that system became vulnerable. The same fixed dimensions that made the carrier work efficiently inside an 8-inch pneumatic line also placed a hard limit on what the line could move. The same dedicated infrastructure that allowed mail to ignore traffic also prevented the network from adapting easily when postal routes changed. The same specialized machinery that gave New York remarkable interstation speed also required specialized workers, maintenance, contractual expenditure, and additional handling. Nothing about that means the system failed. For decades, it did exactly what it had been built to do. It moved suitable mail rapidly between fixed postal facilities while avoiding the streets above. At times, that advantage was enormous. During congestion, it saved time. During severe snow, it preserved movement. Across decades of operation, it became important enough to be suspended, reconsidered, restored, expanded, criticized, contracted for again, and finally replaced. Its disappearance, therefore, tells us something more precise than the usual story of one technology defeating another. The motor truck did not prove that pneumatic transport had been a mistake. It changed which advantage mattered most. The tube still had extraordinary point-to-point speed, but the truck could carry what the tube could not. It could go where the tube did not. It could adapt when facilities moved, and it could perform more of the postal workload without forcing the mail through a specialized network built around fixed routes and fixed dimensions. By 1953, that flexibility outweighed the tube's speed, and so the surviving cylinder is not evidence of a forgotten technology that mysteriously stopped functioning. It is evidence of something more revealing. A transportation system can remain technically successful while the world around it changes the definition of success. We still do not know exactly how much of New York's postal tubing remains beneath the city. We cannot reconstruct every final underground branch from surviving public summaries without consulting the detailed engineering plans and blueprints preserved in the archives, and some historical measurements, carrier capacities, route mileage, total physical tube mileage, remain meaningful only when their different definitions and periods are kept separate. But the central question no longer depends on any of those uncertainties. The network was real, its speed was real, its usefulness was real, and so were the limitations that accumulated around it. The cylinder survived because it could be removed from the machine. The machine itself was far harder to preserve because almost everything that made it powerful was fixed in place: the pipes, the routes, the station apparatus, the contracts, and the postal geography that once made all of them worth maintaining. That is why this worn steel canister feels so strange today. Not because it came from a New York that possessed some lost technology we can no longer understand, but because it came from a New York that once solved congestion by building an entirely separate mechanical route beneath the city, and then, decades later, discovered that the fastest route was no longer necessarily the most useful one.